The only thing I am happy about is this year I pretty much have all the geometry. Now I can move on to pre-calc and get all that up there.
Wait, pre-calc?
Next year?
Oh, pre-calc is hard. I don't know.
No, pre-calc is not all right.
Unless you know the fundamentals.
Yeah, that's true. Alright, in this topic, we're going to cover volumes of a sphere, hemisphere, prism, and 3D objects that come to a point. That's pyramids and cones. But before we can do that, we need to talk about what the parts of a 3D shape. Oh my goodness. I did not know that was going to look that bad. I'm sorry. Oh, what is that? Alright, we're about to run through quite a bit of comedy here. So, I thought Bree got angry and was scribbling out stuff. Like, I don't want to be here. Alright, let's talk about the three parts of every three-dimensional shape. We have the vertex, which is just like when we're talking about 2D. That's where the lines come together. But we're not going to call them lines anymore. We're going to call them edges in 3 dimensions. So, between every vertex, there is an edge. And the collection of vertices and edges makes a face. Where's that tissue box? So, so here on this tissue box, this is a face. Think of a face as the part that you can color, draw on, make your designs. This is an edge. It connects the corners or the vertices. Right? So if you hear me say edge, it's just a line or a corner, right? You would call this a corner anyway. The vertex is where they connect. And the face is where you sell your ad space or your brand. It's a cube. This one is a cube or a rectangular prism. We don't know if it's a cube until we define or are given the lengths of the sides or the edges. Sorry. Now, what was I going to say here? Oh, this is called a prism. This one's a prism because opposite bases or opposite faces are the same.
How do we?
Say again?
I'm sorry. I thought this was a cube.
It could be a cube if we say that each of the edges is the exact same length. We don't know that yet because we can't trust our eyes.
Okay.
So we know. So what Varun is saying is he thinks it's a cube. A cube is a prism, but not all prisms are cubes. So if we had a more precise picture, we could say this is a cube or a rectangular prism. I would say that I think if we were to measure these, it would not be a cube. It would be more of a rectangular prism. Now, we name these by their base. So we're going to do that on that slide, that first shot. Right? Now, these two faces are opposite. This is where we probably should call this Mitchell. This face, this right-hand side, and this face are opposite. So if I wanted to, I can identify this as a rectangular prism because these are opposite. Then the front and the back. And there. Right? All the faces opposite of each other are exactly the same. Let me erase this so you can look at it again. Well, actually, I'm going to go to the next slide. So for it to be a prism, all the opposite faces are the same. We'll say they're congruent. If it's a pyramid or cone, the edges from the base. So for a pyramid or cone, the edges from the base meet at one vertex. And we'll have pictures that you guys will have to draw because I just wasted like 400 pages of toner. And then a sphere is just a three-dimensional circle. If I spin a circle, what do I get from there? So let's look at, this is what you're supposed to see. Not at all what you do see. Now, I am going to upload this presentation along with the video so you can go back and look at it. But here, this is called a triangular prism. If I wanted to try and draw that, I would have two triangles, and then I would connect the vertices with edges. And I can see now, well, you can't really see it.
That's a nice cube. Wait.
You're right, it's a nice cube, but it's supposed to be a triangular prism.
Oh, it's a triangular?
Right, here's base one, it's a triangle, here's base two, it's a triangle.
No.
I'm trying, those dotted lines mean you can't see them if it was solid, that should be behind it. So what you're seeing here is like that.
Oh.
So is it this or something else?
No, it's
Did you like an aha moment or like, oh, you really can't draw a moment?
both.
Both together? Okay, that's fine. As long as it's not a confusion moment, we're good. Was it a confusion moment? No, okay.
When is this thing gonna get uploaded?
Well, now that I gotta piece together 6 different videos because our iPad only has 12 gigabytes of available space, probably tomorrow by the time it renders and uploads.
Oh.
But I will go home and work on that right away.
How long does it make you to edit each video?
When I make them, usually I can answer the whole test in an hour if I take my time, but it usually takes about 3 hours total to make one review video. So 20 questions is about 3 hours worth of time.
Like to load, to make sure the things get loaded?
Oh no, I'm just talking about record, edit, and then tell YouTube to upload it and walk away. Not even waiting for it. It's like 6 hours total. But I'm not gonna count the time when I'm not actually doing anything, so.
Okay.
But let me ask you this, Varun, if I could pick this guy up, rotate it 180 degrees,
Straight.
what would the other side look like?
It looks like a hexagon.
Yeah, we name these based on the bases that are opposite of, why is there hair sticking on that? Sorry, that was weird. These are named, this is your base, and this tells me the opposite side has the same shape. Alright? 2 types of prisms. The right prism, that just means that the edges and the vertex meet at 90 degrees versus not meeting at 90 degrees.
That looks like that. I have a connection. This is the this oblique prism looks like the leaning towers of
Pisa.
Yeah, that one.
Yeah, exactly what it is. Okay, so when they built it, great way to think about it. Obviously, they squared it away. It started sinking. It went from a right prism, and it's slowly becoming an oblique prism.
And then it got stuck.
And then what?
It got stuck in the ground,
Hopefully forever, right?
and then fell.
Now, if I have this shape, and let's say it holds 2 liters of water, and then it starts to sink into the ground, does the volume that it can contain change at all? It's still a 2-liter canister, right?
It's a rigid motion.
Smart man. Yeah, it is kind of a weird motion.
Oh.
Oh wait, is it? Because the angles change.
Oh.
It's a similarity transformation.
Oh.
But what my question was going to be is, if I have a stack of quarters, Chloe, if you really thought my drawings were bad before, wait till you see my stack of quarters. Here's my stack of quarters. I take a straight edge that's square, and I make sure that they're sitting at 90 degrees. Let's say there's 10 quarters here.
That's 250. Oh no, that's
If it was $250,
Just
we would all be looking for quarters right now.
that's $2.50,
Yep.
right?
Yes, sir. So then, Varun tells me, hey, your 10 quarters are worth $250. I go to the bank and they say, here's your $2.50, sir. Out of frustration, I hit my quarters and they're no longer straight, right? They're oblique. Does that change the amount of metal I needed to make 10 quarters?
No.
No. So, if a shape, let's call it a polyhedron. That just means 3-dimensional shape. Let's just do the whole thing in one shot. Now, some of this may not make sense just yet. If two three-dimensional objects have the exact same area for their base and the same height, then their volume is equal. Cross-sectional area means if I have a cylinder, radius 2, height 3, I can find its volume.
Wait, I have a question.
Yes.
The formula of a cylinder is like 1/2 height. Is it height times 1/2 times something?
It's on the next slide, which is blacked out. Or one of the next slides. I'll show you.
Does it say after cross?
Sectional areas, then,
I thought that said purpose. Something purpose.
where?
Cross something purpose.
Cross-sectional areas. That was to distract you from using the wrong there. You guys did that on the video. Make this one a 9-hour project. Then their volumes are equal. I'm playing in the black so we all can look at my mistake. So, if I take this cylinder, and we'll find the area of it, if this meets the base at 90 degrees, and then maybe I sit on it and it warps it, so that now it looks like this. This went from a right cylinder to an oblique cylinder. It still has radius 2, and if I drop in altitude, it still has height 3, right? It's still going to have the same volume, it's just deformed.
Wait, I have a question.
Go ahead, sir.
Wait, I heard something when you said about like this is a similarly transformation. If this is a rigid motion,
Is it a rigid motion though?
Because-
The angles change.
I thought you said rigid motion saying that like it could move anywhere, but
No, rigid, yeah, it can move, but it can't change size, angle, shape.
good angles.
So, Varun, let me see. Let's do it with props. You're gonna help me out with it, okay? I'm sorry, you keep being the head. You can sit there first. Okay. So, I need you to have this first. Please hide that. Nobody knows he has it, okay? Hide it. That's the opposite of hiding. You're still showing me. There we go. Okay. So, I have this marker, then I throw it to you. You gotta catch this. Stick it on your pocket or something.
Okay, I got it.
Ruin your crap under the pressure. Now, I have this expo marker. I'm gonna toss it to you. I translated it, rotated it, you reflect it, right?
Yeah.
Now, that's a rigid motion. Ruin, hold the marker up for everyone to see. Beautiful. Same size, right? Same shape, everything's the same. That's a rigid motion. Ruin, throw it back. Oh, that's a good. Now, Varun, nobody's gonna hear this. When I throw the marker this time, pull the big one out, okay? But don't do it yet, they gotta see you catch it. Alright, Varun, ready? Now hold that one. Look at that, it's still the same shape of a marker, the angles are the same, but that's much larger, right?
Yeah.
It's stretched, it's gotten bigger. That's a similarity transformation. It's the same shape, but it's a new size. Go for it, don't break them off.
I'm sorry, actually, it just went.
Varun, if the teacher tells you to throw something, nothing that breaks is on you, it's on me. You're fine, man.
I tried to throw, but then the air velocity air.
This is why I didn't throw these for you. So, but look, pretend Varun throws this out, right? But when I catch this, that's a similarity transformation, right? It got smaller. But if I catch these, then it's.
But it's but I have a question. I'm just curious. I'm just acting curious. But isn't it like the air, the force of the speed comes there, and then you try to, and then the thing is this air resistance goes there, right?
Can I tell you something in pure honesty?
Yeah.
The reason I'm teaching math today and not physics is there's too many rules in physics. In math, when you get stuff, you just get to make up stuff like, oh, add a dimension, like we talked about earlier.
Yeah.
When you talk to Mr. Allen about that, he can't go, oh, Varun, add 2 more dimensions and it'll make it easier, right? Because how do you work in the 5th dimension in the real world? I have no idea how to answer those types of questions, man.
For some reason, in math is in science is math. That does not make sense.
In science, there's math?
Yeah.
Well, we'll talk about that in the future. I don't want to waste our last 40 minutes. Okay, so this is what I was trying to show you. I don't have these. I found this on the internet this morning. This is that page. Okay, you can read. How does yours? But look at Vermon's. The prayer play favorites. Okay. Sorry. Here, just flip it over. Right. So, how many CDs do we have here? 1, 2, 3, 4, 5, 6, 7, 8. You say 17?
I think so. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
Bree, how many do you have?
18.
Yeah, Bree has one. One massive rectangle. Alright. So, if I took these CDs and I filled each one up with water, right, we would find their volume. We'll call it X inches cubed for however many cubic inches. Would there be a different amount of water that I would need to fill this one up? No, it's the same, right? Because this is a right prism. This is an oblique prism, but they still would hold the same amount of water. I'm going to say the name wrong. I know it because I've never heard anyone pronounce it. I've just read it. This is Cavaliere's principle. And that's just saying if a shape has the same height and the same cross-sectional area, they'll hold the same volume. Nobody knows what cross-sectional area means. And this is what we're going to talk about.
Is that predator monitor?
Say it again.
Is that predator monitor?
Say that again.
Is that predator, like the monitor?
Where?
That thing there.
This?
Yeah.
Bruno, this is a CD case, man.
Oh.
That's what I want to show you what cross-sectional area is.
Oh.
Oh, you mean here? Like
Yeah, the thing, the whole thing.
No.
That looks actually, I'm not lying, that actually looks like a monitor.
Alright, I remember when my teacher, when I was in high school, was talking about having records, and I was like, this old guy. Now I'm talking to you guys about having CDs. When's the last time any of you held a CD? Okay, once.
Mine was 2 months ago.
Have you? You still use CDs? Do you actually use them though, or do you have them like a collector's item? You have them,
I have 81-inch TV that can just put CDs in.
Alright, so way back when, we used to have these discs that would play music, and then we got MP3 compatibility. You go 600 songs. Now you can just stream whatever you want. But this one right here, we're going to talk about, these are a standard size. If I were to look down on this stack right here, this would be my view. I would have this length by this width. This is called your cross section. I can pick up any of these, and I would look down and see the exact same shape. I would be looking at this right here. So whatever this area is, each of these is going to have the same area, right? From looking down. Well, the height is 17 CDs. So if I want to go into the third dimension here, oh jeez. This is setting me up. Alright, that's my CD tower. Please believe me. This is my cross section. I can look anywhere in here and I would get length and width. This is called cross-sectional area. That just means at any point I can cut into here parallel to the base, remove it, and when I look down, I'll see this shape.
Oh, that looks like a CD. Now I actually know. I thought it was such a...
I'm glad that my artwork helps you see this. Now,
I'm running with how the brain works.
I'm going to take the area of each CD and multiply it by how high it is to give me the volume of this prism. Alright? The area is length times width times the height will tell me the volume of that stack. Now, for a prism, any volume can be found by taking big B times H, where big B is the area of the base. So on this one, I can see that the cross section, there's a quadrilateral. Quadrilaterals have area, length times width. So here you can see that the formula for the area was substituted for B, and then I can multiply it, and that will tell me the volume. Say it again, sir?
No, never mind. I was just saying.
Okay, or in Varun's case, the number of creditors.
No, that's just a CD. I finally realized after my brain started working.
Is this the part that you saw was predator?
No, I thought, yeah, that's
Okay.
And then I thought, oh wait, is this actually a predator? And then I saw when you said that when you remove the CDs, this will face up, and I saw that, and I said,
Gotcha, okay. So we kind of get that. Let's see if we can come up with the volume of.
well, I have an idea. So any stack of items, like if you remove, it will be like that.
Say it again?
Like go back to the CDs.
Yep.
That like CDs can be like an example, but like it can be like anything, like a stack.
Anything that has the same area when you look down on it from the top that you stacked up, you can do.
So like basically a piece of paper.
Perfect. If you guys look at that thick old packet, right?
Yeah, here.
You have all 50 sheets on top of each other, and you want to know the volume of paper. It's going to be 11 by 8.5 by, that's the size of a standard sheet of paper,
Yeah.
by whatever the height is when you stack it up when you're looking at it this way. Here's your packet. 8.5. This part's 11. How tall is that? An inch? So I can do 8.5 times 11. That's 88, 93.5. I don't know, I'm making that up. Is it 93.5?
88.5, I think.
93.5. And then the height's 1 inch. So then this is going to be 93.5 inches cubed. That's how many trees, that's how much of a tree we had to force out and then onto your desk. I can do that because the sheet of paper, every time I pick up one sheet of paper, the next one has the same area when I look down on it. So I just need to multiply that area by how deep it is, and that'll give me that answer. Oh.
Right, those formulas would we have to memorize?
So that's what I wanted to talk about. That's why I have them this way. Let's talk about the types of prisms I normally see.
Rectangular.
Perfect. So for prisms, rectangular, triangular, quadrangular, no, a cube, circle, sorry. What do we call a circle prism? Say it again?
Here.
Sphere?
Careful, that's why I asked. A prism means that you take two bases and connect them.
Cylinder. Oh yeah.
And the reason we can't say sphere, where's the base there? I guess the easiest way to think about finding a base is if I set it on a ramp, would it hold still? That's where your base would be, right? This wouldn't be your base here. If I set it in this orientation, it would roll. So,
This is a cylinder.
huh?
That's a cylinder.
It's meant to be a cylinder, but it's not supposed to actually a cylinder. And then this oddball one would be trapezoid.
Oh, trapezoid. Wait, trapezoid isn't a 3D. It's in a prism,
Well, so that goes back to the whole idea of how do we name prisms? We just name the base and then throw the word prism after that. Here's a room. What shape is this base right here?
It's a
Rectangle.
rectangle.
What's this one?
It's a square.
What?
Wait, it's a rectangle.
It's meant to be the same, right? So what kind of prism is this?
A rectangular prism. This looks like a square for some reason.
I don't know if I try to draw a square, it looks like a triangle. It's just, yeah. We're talking about in general. Now, know the areas for these.
I know, and try.
I would say some of us will know all except for the trapezoid,
Yeah, trapezoid.
which I think is A1 plus, or B1 plus B2 divided by 2
A plus B equals square.
times the height. I don't remember.
A plus
But these are the most common. This one is going to be release on. Here, this is length times width. This is 1/2 base times height. For a cube, it's just the length squared since the base is a square.
I'll write this down right now.
Prism base area. And for a cylinder, the base is a circle, so it's pi r squared. Now, with just that information, you can find the volume of any of these prisms with this. Say again?
Does the height not matter for the cylinder?
These are just the base area. I added that after the fact. But yeah, this is just for the base area. And why I wanted to do that is, I guess we could just make, let's just do this. I don't like that. Well, oh, that's it. So this is what would happen if we take B equals BH, and in parentheses are all of my big B's, and then H is just packed to the end. Don't want to double up on this, but everyone has been learning since second grade that 1/2 of base times height. So this is just basically, let's call it A for altitude. If I dropped in altitude, what would that be? Say it again?
Would that be your oblique?
Actually, this works for both. Since we know through Cavalieri's principle, it doesn't matter if it's oblique or right, they'll have the same volume. This works for both. Now this only is the rules for prisms, that we do B times H. Now, hopefully I made enough of the room. Yeah. So for this one, this is a rectangular prism. This base and this base are opposite of each other. This base are opposite of they're rectangles. So if I had 3, 2, 12, and I wanted to find the volume, the area of the face, or the base, sorry, is right, well, this one's highlighted in red, so let's make that the base we're looking at. This part is 2, this part is 12, so big B times H is length times width, which would be 2 times 12, times the height. This way, because I'm calling this my base, the height is orientated this way, be 3, that'd be 24, 48, 72. Now, what should happen is, if we're not looking at that as my base, so let's get rid of this, and let's do what makes a little bit more sense, and let's call this my base. Here, length big B is going to be 2 times 3 for length times width. And then my H becomes 12. This just becomes the fanciest 8 I've ever drawn. 6 times 12 or 72. We get the same thing because this is a fixed volume.
6 times 12?
Yes, 32.
You have the parentheses on the 12 and less than that.
Oh, yeah, I do. I'm just.
The list on the left was the base area, so on the right, where
Yes, this is the. Let's do this. This is 2D. Right, length times. This is the polygon. This is the polyhedron.
for cubes is that cubes on this side and on that side of the square.
Yes.
Just added it.
Yep, because the area of the square would just be the same thing. So like if this is 2, it'd be 2 squared. But for a legitimate cube, which seems to be the only shape I can halfway with, it's just going to give me length times width times height for 2 cubes. So the whole idea here is this has a fixed volume. If I set it on its side this way, it's going to hold the same amount of water if I rotate it so that the red's at the bottom. Shown it two different ways, and those work. Now, anything that comes to a point, we still get to use the same 2D rules, but we're not talking about prisms anymore, are we? This base is not the same as that point. Now, there's like 12 people in the room, and of those of you who I see in calculus, one of you may remember to ask me this question. But using this, there's some stuff we can do in calculus to just get this. And if you remember it, I'll show it to you. Then once you have that understanding, you guys know Eric, he finally came back to me and asked after 4 years. And I'm glad that it made sense to him. So on this one, if it comes to a point, you use C. Am I walking you, sir? Yep, that's all you need. If it comes to a point, you're still going to use big B times H, but you're going to divide it by 3. 3.
So isn't it 1/3 BH or 1/2?
It's 1/2 for the area of a triangle, right? Well, let's see this, just to double check yourself. If I have a square, right, that's length times width, a triangle would be half of the area, so I can just do length times width divided by 2. So yeah, it'd be 1/2. So, here, because it comes to a point, we're going to divide by 3 when we find the volume. So you can do the same thing. What's the formula for the area of this base? What shape is it?
It's a pyramid.
Yes. It's a quadrilateral. So what's the rule? Say it again. Yeah, length times width. So whatever L is times whatever W. Where in the world do we get our height from? This is what I meant by drop that altitude. Start at your point and come straight down at 90 degrees. However far that line it has to travel, or what the length of that line is your height. So this is going to become LWH divided by 3. So let's set this up. Let's erase this and call it 4. Let's erase this and call it 3. And let's call this 6. So, for this one, I'm going to end up with 4 times 3 times 6 divided by 3, which should be 24. Oh.
What about the questions that don't give you the height of this length?
Say what?
The questions that they don't give you the height, they give you like this length.
So let's look at that one. First, before I do that, does everyone understand why this is 24 cubic units? Good, Varun. Renee, are you okay?
Yeah.
Okay, yeah. I know it's like the longest math class you've ever, but you guys did this voluntarily. So, all this question was, if I drop this altitude, where did you say the missing part was? At the altitude or the hypotenuse, or?
No, I got like when it wants the volume, but it gives you this lengthy height.
Yep. So it's this, but it wants the height. Perfect. Okay, that's what I was double checking. And then it tells you something like, did it give you that in the problem? The length there? I'm trying to remember that problem. You have to have 2 of the 3. If it wants this and this, it would have to give you this, right? Or, yeah. Do you remember the exact numbers? If not, I'm just going to go off of. Okay, that would work too. So, any questions on how we got 24 there, though? Pretty easy. You can see that I cheated a little bit by making sure 3 was in the numerator so I could just clear it out.
So say it wants the volume, and
Mhm.
maybe this number, and this number, but then also volume.
Oh, okay. So you know, like, oh, but it had to be a square pyramid then, right?
Yeah.
It was a square, okay. So we have a square pyramid, you know the slant, and it wants the volume, is that right? Okay. So, for this one, I'm gonna go ahead and draw the height and label it. Now, from here to here, if I cut this as a cross section, I'm gonna end up with this triangle. And then I want that height, right? So I can use the Pythagorean theorem here. No, it's not gonna ask you guys, so let me go over that. And that will give me a height of 4, and then I can do the volume. So yeah, if you get stuck there, if they're asking you to find something, try and see if you can come up with a cross section that'll make it easier for you to work it out. Any other questions on the pyramid? This works for a cone too. If I had a cone, cone is just a cylinder whose radius at top is 0, so all of this is negative space, or not used. This would just be pi r squared times the height of the cone. And then we go to this, and then topic 2 we can go through really fast, I promise.
Yes. This is topic 2 is my favorite. I'm not sure.
That's why we can go through it so fast, it's everyone's favorite.
I remember this.
What I want to do is talk about how these are related. The volume for a sphere is 4 pi r cubed over 3. How would I find the volume of a hemisphere? Or how would I get that equation? Breathe.
Wouldn't you just say 2 r squared over 3?
How did you know it was a 2? Because I showed it to you already? How did you get to this?
You did that.
I did show it to your
I
class,
wasn't
yeah.
paying attention though, but.
Wow. I mean, yeah, I guess you're not gonna have my math class next year, so I am gonna make sure that you know. But anyways, so you weren't paying attention in my class, but you are paying attention now. How would you know that 4 becomes a 2 and that's the answer?
Because the hemisphere is half.
It's half of. What does half of mean mathematically?
Diameter. Radius.
Close. Go way back. What's half of 4?
2.
How did you do that in your head?
What about it?
Or multiply by half, right?
Yeah.
So if it's half of, what are you getting at?
I have a question. I'm just curious.
You go for it.
When you multiply half with the number, why do you get a less number?
You have 2 $10 bills on you?
No.
Do you have any money on you?
No.
Do you have anything of value? Okay, let's see. I like your shoes.
No, I have money.
Oh, you can borrow 2 of your bills real quick.
I have one.
You only have 1?
Yeah, one.
Can I tear it in half?
No.
Okay, can I borrow your shoes?
No.
Okay, let me just put it this way. How many shoes do you have?
2.
If I keep half of them, how many do you have?
1.
That's why it's less.
Okay.
Sorry, I was trying to make a little extra money in there.
I'm trying to calculate that.
So, Bree said half of this is that. So half means multiply by 1/2. I'm going to get 4 pi r cubed 6. These are both divisible by 2.
You're writing it better.
Huh?
You're writing it better.
Throughout the day, or you mean since the tablet?
Right now, like, it's good.
Oh, just like right now?
Yeah.
That's just because Bree put magic on it.
Hey.
No, because I got to send this video to her mom at this point when she said I wasn't paying attention in your class, and I want to make sure it looks
Oh,
good.
don't see that part, right?
That's right, and you're right by the camera.
You could delete that.
I got her number. I texted her like yesterday.
Oh.
Every time I say half.
Hi, Miss Jones. Becca says hi too. All right. So that's how we get to there. If it's, you can break these down. If I said what's the formula for half of a hemisphere, you would just multiply this by half
You got a
again.
sector.
You're getting there, but that's way later. That's cut through.
And that's actually a sector right there, the whole circle.
It kind of is, but in 3D instead of 2. Now.
Oh,
and
yes, sir.
to topic 2. Only because we are running out of time, we're going to go a little quicker.
Let's go.
Before we do anything, what does the vertical angles theorem tell us? Don't say I forgot. Which ones are congruent?
Is it angle 1?
Yep, the opposite ones. If two lines cross, the opposite angles they generate are congruent. From that, we can do all topic 2 in 6 minutes.
Side, same side, interior.
That's what we're doing, yep.
Oh,
So, if I add a second line, the vertical angle theorem, because these have, no. If I add a second line that's parallel to the first, these are going to be equal. These are going to be equal. Topic 2 is done.
Okay. You
Back
done?
up, we're done. No, obviously I'm going to elaborate more. But, doing the vertical angles theorem and then adding that second parallel line, just by these markings, if this is 30 degrees, what's this one? What's this one? What's this one? Alright, not to put too much stress on us, but right here is a straight angle. What's this angle then?
That's 30. Oh, it's 150.
I heard 150 over there, right? Straight line, 180 degrees, 180 minus 30, leaves me 150.
And then that other one's 150. Because that's also congruent. And then that's 150. That's 150.
Now, we did all of that based on the vertical angles theorem. And I'm okay with that, but how in the world was I allowed to say that this and this are equal?
Oh, because.
Nothing in the vertical angles theorem tells me that.
Because.
Well, let me ask. Well, let me ask, Paula, how do we know these two are equal? The lines are parallel, but what theorem tells us that we can say those are equal?
Same side, interior.
And that becomes the whole question of topic 2. So, keeping in mind what this is, let's look at why this is true. Also, if you guys did the quarter 2 writing assignment, a lot of flashbacks. Oh, did I really do this just right? All right. How lucky are we? I don't have to rewrite anything.
I did not like the first two. That was not the best assignment.
I'm sorry, man, but I enjoyed it. Same side interior angles, yes. SSIAT.
Okay.
Same side interior angles. We have to talk about how do we determine if they're interior or exterior.
Wait, how is this? Oh, angle Theorem. Okay. It says, I thought it says same.
You thought you saw a bad word?
No, not bad. I'm just saying it's. I thought it's spelling wrong.
Oh, yeah, no, in this class that's definitely a possibility.
Just
All right, when we talk about same side versus exterior, it's talking about where do they lie in reference to the parallel lines. This is inside the parallel lines, so it's the interior. This is outside the parallel lines, it's the exterior. Alternate versus same side does not worry about the position or where they are as far as interior exterior. It's what side of the transversal are they on. These angles are all on the same side of the transversal. These angles are all on the same side of the transversal. So if we just with that knowledge, same side interior means they have to be on the same side of the transversal and they need to be inside, right? Which is, say it again. Say that one more time. Yeah, we're gonna, so yeah, let's do this. If we started with our original vertical angles, we add that extra parallel line. Same side interior angles are supplementary. What does it mean to be supplementary? They have to add up to 180, right? What I said to you guys earlier is, yes, we know this, but we had nothing that said these vertical angles, would have to be the same as these. Same side, so that's over here and on the interior. That needs to be in this area right here. They add up to 180, so I can say 150 is going to leave me with 30. And that's our first step to saying that this has to be the same. Now we can use the vertical angles theorem and fill the rest of this chart out. 30, 150, 150, and we're done. My whole thing is, yes, we know the vertical angles are congruent. We know vertical angles are congruent. We need that one extra piece of information to show that they are congruent to each other. By same side interior angles, these must be supplementary. And that's how that works. Now I'm going to move to corresponding. This is the one that I was asking about originally. And of course it doesn't quite line up. But we can do this with just the same side interior angles being known. Varun, pick an obtuse angle for me.
Ready?
As long as it's over 90 and less than 180.
181. Wait, no. 100 and
We're going to go 182.
52.
152. All right.
152, 152. These are the same thing, right?
That would be, but let's worry about the corresponding. So, let's ask this question. Varun, what's this angle down here?
What?
What's this one right here?
Is that 152?
This is a linear pair, right? This line is 180. So how much?
No, that's 180, 152. That's at least
28.
Yeah, 28.
Perfect. Now, same side interior angles have to add up to what, Varun?
Same side interior has to equal to 180.
So what does this one have to be?
180.
The
Wait,
sum.
no, 28.
Well,
152.
152. Varun, you're always welcome to take a minute to think the answer through. We don't have to have immediate response. All right. Now, I've shown a way to link through the linear pairs theorem. If I know this, I can get this through linear pairs theorem. From here, I can get same side interior angles. And now, if I erase this, it's showing me that the corresponding angles are congruent. Now, if you're not in my class, I want to spend a second on this. Let's make this a little easier. 130, 50, 130, 50. Now, the way I do this is I like to look at these in two boxes. I put a box around my first vertical angle. I put a box around my second vertical angle set. The top left box is equal to the top left box. That's 130. The top right box is equal to the top right box. That's 50. Guess what the bottom right box is equal to? Oh yeah.
Same thing.
Yep. And look, the vertical angles theorem is falling out from this. Bottom left. Wow. 50. All right. So that's how corresponding angles work. And the nice thing is I can put these up in any order. I use same side interior angles first. And then from that, we were able to prove corresponding angles. All right. What do you guys think AE, AT means? Alternate exterior angles. So, these are not supplementary. These are congruent. Make sure I erase that. So, alternate means opposite sides, right? No, that doesn't work. Well, I guess we can do this. They're on opposite sides of the transversal. We have to switch sides before we do it. Exterior, this still holds true. We don't need to memorize this again. Same side means they're on the same side of the line. Alternate means we have to cross over the line. So, if alternate exterior angles are congruent, if I told you that this is 45, and let's label these. 1, 2, 3, 4. Which angle is the alternate exterior angle to this? Abby. 4. Varun, do you agree?
Yeah.
Sydney, do you agree? Well, yeah. This is the exterior. This is the exterior.
Wait, what? It's supposed to be alternate.
Yep, and from here to here are on alternate sides of my transversal.
Same side exterior angles is the same as this thing, but the
Alternate interior angles would be inside, but
the exterior is this.
Let me give you one. Huh?
Wait, what's the 1, 2, 3, 4?
I was asking which one. Just put 45 or 40. I was asking which one would also be 45. Sorry, let's go ahead and put that in. That would be 45 degrees as well. Alright, go to the computer.
Oh, impressive.
What's that?
You put your mouse on the top of the thing.
Oh, yeah.
And then that was impressive.
I didn't know if you were saying like I was tall and that's impressive, or if the wireless. I was just. Now, parallel lines there. This one's too easy. If two lines are parallel to the same line, they're parallel to each other. This silver bar and this silver bar are parallel. And they're parallel to this, right? Since this is parallel to this, and this is parallel to that, that is parallel to this. That's all. It's just parallel lines never intersect. No matter how many you have, as long as they're parallel to each other, they never cross.
6 more minutes.
Maroon, you're making me nervous. I think my keyboard died, not that I broke the computer. Alright, this one makes sense as well. If I have two lines that are perpendicular to the same line, then those two lines are parallel. Going back to the board, this is a 90-degree angle, meaning that this line here and this one are perpendicular. Here, this silver and this are perpendicular. That means the silver lines on my board are parallel. They're just ones that I want to cover. If you're confused, raise your hand, but they're pretty straightforward. It's just nice to know these because these are those little tricks that if they're fresh in your mind when you get to the test, they may help. All right.
9 more slides.
Huh?
9 more slides.
9 more slides. All right, so let's ask this question. What is the sum of the angles that are interior of a triangle?
180.
What's the measure of a straight angle?
180.
So I can see that the measure of angle 1 plus measure of angle 4 is equal to 180, right?
Yes.
I'm just going to write it as angle 2, angle 3, angle 4. What do those add up to?
Well, that equals to 180. 380, right? 180.
Okay. Are you ready?
Yes.
Okay, let's do it this way. If these are both equal to the same thing, can't I say angle 1 plus angle 4 are equal to angle 2 plus angle 3 plus angle 4? Do we agree with that?
Yes.
Okay. What can I do algebraically to kind of solve for angle 1 here?
System of operations, right?
We could make it that hard, or we could just subtract angle 4 from both sides.
Oh yeah, you can do that.
And that tells me angle 1 is equal to angle 2 plus angle 3.
If you substitute it with values, like it's gonna be like 2 plus 2.
Oh, don't do that hard, man. We only have 2 minutes left now.
Okay, let's go.
So, all that's telling me is the remote, this is the remote interior angle term. These two angles will always add up to be the outside. So, if I know that this is 70 and this is 40, I know that's 30. Then I can find that. Or I can just say 180 minus 70 is 110. I wanted this up here because I didn't put this theorem by name, but I kind of showed you why it works. So the inside of a triangle adds up to 180. Straight lines add up to 180.
You check something. No one.
All right. Does anyone have any questions on congruence? We kind of spent a lot of time on similarity. It's the same rules, except for you also have to verify that all the sides that correspond are equal. So let's do this. By side, side, side.
Topic 4 now. Topic 4 is the least.
Varun, are these congruent?
Yes.
By side, side, side?
Yeah. I got that, sorry.
Yeah, if anybody needs to run, nobody should get in trouble for being tutoring. And if everyone ends up on them, I'll take that as a cue to.
I got
No.
that, sorry.
Let's do. let's do this. To supplement the rest of this, these videos are on my YouTube channel as well as topic 1. I was going to ask everyone, just look over topic 1 briefly, just to understand contrapositive and all that. Those are my newest videos. I went into the most detail with them, so I didn't want to cover them today if we didn't have time. With that, so no one gets in trouble and we can't split up because I have to be with everyone at all times. Let's go ahead and pack up and get ready to head down to the library so we're not late.
Oh my god, after 6 hours of studying